Okay, here we are, ready to do it. We're going to take the results of the last couple videos and put them to the specific case of Kepler's equation or Kepler's law, which involves Newtonian gravity specifically. So we're going to choose a central potential, particularly this central potential. This is the Newtonian gravitational potential energy. It's negative, it's attractive. Big G is Newton's constant. M1 and M2 are the two masses that are attracting each other. And then it is an inverse square force, which means it's a 1 over r potential. For shorthand, I'm going to call this constant up top kappa. The reason for this is it turns out that the electrostatic Coulomb potential also has this same form except for the plus sign, but a different numerator with some k's and q's or something like that. And so I want to leave this kind of general. We can kind of do the gravitational attraction problem and the electrical attraction or repulsion problem all at once. The classical orbits are going to be the same because they have the same dependence on that separation distance between them. One last reminder, the mu here is the reduced mass of the system. Usually that'll just be the mass of the lighter object if one of them is very heavy. Capital L is still our conserved angular momentum of the system. R is the separation distance between the two objects, which again, if one of them is very heavy, is pretty much just the distance to the center of mass. And then phi dot is the angular velocity of the of the reduced mass as it goes around the center of mass. The last thing I've got here came from our previous video. This is the Binet equation using this substitution lowercase u, which is 1 over r. You can see a lot of 1 over r showing up here, so it's kind of convenient. And we said that you get this nice simple harmonic oscillator type equation. The right-hand side's a little complicated, but it's just the u derivative of the capital U, the potential energy function, evaluated at r with some constants out front. And that's actually where we're going to start our analysis for Kepler gravity by trying to solve this differential equation. And we'll see it's actually not so bad. We put in a lot of work to get the Binet equation, and it's quite nice for the Kepler problem. Okay, so let's go ahead and do that. Notice that if this is our definition of capital U, this is the same thing as saying negative kappa times lowercase u in terms of this reciprocal variable. That also means that if I go take my derivative here, u of r, which is of course u of 1 over u, becomes minus kappa u here. And when I take a derivative of minus kappa u with respect to u, the negative signs will cancel. Derivative of u is just 1. And I'll end up getting mu kappa over L squared, a positive constant. And now we can see kind of why this is really nice. The right-hand side is just a constant. Now, it's not 0, which would have been super nice, but we can make a very easy transformation to make it into a 0. Let's write a new function. I'll call it w, which is just u minus this constant. And the reason why that's going to be kind of nice is because the second derivative of w with respect to phi kills off the constant. So w double prime and u double prime are the same. But then when I plug in this u, which of course does involve w plus this constant, the constants will cancel on both sides. And so I actually end up with a very simple differential equation for w. This is the famous simple harmonic oscillator equation, which of course is, well, very easily solved. So the solution here, I won't belabor it again, is some constant. I'll write it as a cosine again of phi minus phi naught. The frequency here is 1 because the leading term of this w is 1. And then the two unknown constants of integration are, I'll call them some kind of amplitude and some kind of phi naught. We'll kind of wrap those up into more useful constants in a little bit. Now, of course, this is w. I actually want u, so I should add on this extra constant mu kappa over L squared. Okay, we're almost there, but even that's not really what I'm looking for. I want to know the orbit as in r as a function of phi, which is the reciprocal of this. So I'll just flip it. So this is a little clunky. We would like to do a couple things to try to simplify this or write it in a more useful form. This is actually kind of the answer, but it's going to be a little more convenient to rewrite a few things. First thing we're going to do is let's just decide together, you and I, that phi naught is 0. This just amounts to choosing an overall orientation of our polar plane, and it'll just be convenient to just pick a particular direction to be the starting direction. Notice that phi naught really does mean the initial angle of my orbit, and why don't we just pick that to be 0, meaning somewhere on the positive x-axis. If you chose it to be something else, it's just going to rotate the whole picture around, but it doesn't change the qualitative features. So we'll set the phi naught to 0. The second thing we want to do is I'm actually going to factor this sort of strange constant out of the denominator, and then this a thing times that constant I'm going to call another new constant. And so I'll end up with something in the numerator, something that has appropriate units, by the way, and we'll have something in a slightly more convenient form. Okay, here it is, the general form. Like I said, I set phi naught equal to 0. I pulled out this kappa mu over L squared from the denominator, but of course that puts it in the numerator as an L squared over mu kappa. The A thing, lumped it together, called it some new thing, epsilon. And what we see here is actually the polar form for conic sections. That really is what they look like. This P here is called the semi-latus rectum. Semi. We'll talk about the geometrical interpretation of that in a later video. This epsilon here is the eccentricity. And it basically tells us how kind of squished the conic is. It also classifies the conics. So I'll give you a little bit of info about that over here. If epsilon is literally 0, we have a circular orbit. And you can kind of see that that would just make r equal to a constant, which of course, yeah, they can't get much more circular than that. If epsilon is between 0 and 1, we get an ellipse. And we'll take a look in a bit about, okay, what does that ellipse look like, where are its foci, etc. But we already kind of knew from Kepler's first law, or I guess we didn't know that yet, but Kepler certainly knew that the planets and other orbiting bodies around the sun all had conic sections for their trajectories. A circle is sort of a very, very simplified ellipse. Generally, we're expecting something a little more elliptical. Earth's eccentricity for its orbit is very close to 0, so it's practically circular, but we could have some very long elliptical orbits that have an eccentricity much closer to 1 for things like distant comets and maybe Oort cloud objects. If epsilon equals 1, we get a parabola. Now that's not a bound orbit. That's something that comes in from infinity, swings around, and then goes back to infinity, just barely. And then if epsilon is greater than 1, we have a hyperbola. And that's also an unbound orbit. That one swings in fast from infinity, zips around, say, the sun, and then flies back off. Again, we'll look at more of these details later on. The missing bit here is, okay, I can see how P, the semi-latus rectum, is defined in terms of angular momentum, and then some general properties of mass, etc. But where does the eccentricity come from? Can we get a formula for eccentricity in terms of maybe something else that's given in the problem, which is, say, the total energy of the problem? That's often something that's useful to write. So let's try to rederive what the eccentricity of this orbit is in terms of the constants of motion, the angular momentum, and the total energy of the system. Okay, to do that, I do want to go to my energy equation here, but I've got an r dot. And unfortunately, r dot is not easily found from this because this is my orbit. This is r of phi, not r of time. Luckily, the chain rule comes to our assistance once again. R dot, which is dr dt, of course, can be expanded out using the chain rule as dr d phi times d phi dt. But of course, d phi dt is phi dot, and we do have a way of expressing phi dot in terms of L and R. So this will be L over mu r squared times dr d phi. And now I can take that and plug it in directly for my r dot here. So let's see what that looks like. And then don't forget that our mu of r is actually minus kappa over r. Okay, so here's our expression for the energy. We're ready to do what we can here. Obviously, taking the r derivative with respect to phi, or taking the derivative of r with respect to phi won't be too bad. I've got a 1 over r squared, but I know what r is, and actually 1 over r is going to be even nicer. I've got a 1 over r squared here, and I've got a 1 over r here. So first thing we should do is probably take dr d phi, because we have to plug that in here. And I'm just going to think of this as a chain rule type thing. So the p is a constant. This whole thing is to the minus 1 power. So when I take its derivative, I'll get a minus 2 with a negative out front. The derivative of the inside, of course, is going to be, well, epsilon is a constant. Derivative of cosine is negative sine. Okay, when I plug this in here, however, some nice stuff is going to happen. First of all, this has a 1 over r squared, sorry, not a 1 over r squared, 1 over this binomial squared, but r squared itself has a 1 over that same thing squared in it. So when I go plug these in and try to expand, we'll have an L squared over mu squared, sure, but this piece right here is going to have all of this junk squared. The negative signs will all go away. I guess they did anyway. So I'll have a p squared, epsilon squared, sine squared phi. This thing, though, in the denominator is going to have 1 plus epsilon cosine phi to the 4th power, because it's a negative 2, and then we're squaring it. This bit right here, however, is 1 over r to the 4th, which is 1 plus epsilon cosine phi to the 4th over p to the 4th. And we see this wonderful cancellation here, where this whole quartic power goes away. We can do a little bit more, actually. Those cancel. 2 of these powers cancel. So it's real nice. The next term over also looks kind of nice. I have an L squared over 2 mu. The 1 over r squared here also will look kind of pretty. I'll have a 1 plus epsilon cosine phi quantity squared over p squared. And then the last term, well, not much we can do about that. It's just going to be a kappa over p. But at the end, the same binomial. Now let's look really closely here. This and this both have the same kind of coefficient out front. L squared over 2 mu, and then there's a p squared in both, so I'll factor that out. This term, however, is going to have an epsilon squared sine squared phi. This term is going to have 1 plus epsilon cosine phi squared. And then there's this term, but let's rewrite it as well. Notice that kappa, because kappa didn't show up anywhere over here, so let's just write everything in terms of the others. Kappa is what? L squared over mu p. So this is going to be L squared over 1, not 2, but 1 mu p squared times 1 plus epsilon cosine phi. And hopefully now you can see what's about to happen. I'm going to go ahead and multiply and divide this term by 2. The whole thing out front can be, again, brought together. I'll have an L squared over 2 mu p squared. When I expand out this binomial squared, I'll end up with an epsilon squared cosine squared plus an epsilon squared sine squared, which will just give me an epsilon squared. This 1, well, will give me a plus 1. And then this binomial squared will also give me the cross term of 2 epsilon cosine phi. But look, I also have a minus 2 epsilon cosine phi. And don't forget, there's also this minus 2 times 1. And lo, it was good. Those cancel out. This 1 and this minus 2 become a minus 1. And I can see that this is actually going to be pretty nice. I'll go ahead and multiply this whole thing over to solve for epsilon squared minus 1. Or actually, I'll add the 1 over. 2 mu e p squared over L squared. Phew. Okay, a little messy. And of course, I can rewrite this a bunch of different ways because I know that P can be related to L and kappa. That's probably the more convenient way to write it. Usually kappa is kind of the more given thing here. So I'll write this as 1 plus, oh gosh, what'll that be? Okay, so it's P squared. So the L squared here and here do not cancel because it's P squared. I'll have a L squared upstairs. There will be a 2 and an E. What about the mu's? There's a 1 over mu squared that comes here, so I'll have a mu in the denominator. And then there's a kappa squared in the denominator. So that's probably a slightly more convenient way of writing that. Notice you'll take the square root, the positive square root, to get the actual eccentricity, given in terms of the total energy and the orbital angular momentum. Notice that if the total energy is 0, I recover my parabolic case, so that's kind of nice. E has to be less than 0. All the rest of this stuff is positive, but E has to be less than 0 if I want to get something less than 1. And indeed, circles and elliptical orbits are bound systems, so their total energy is less than 0. And of course, E will be greater than 0 if we have a hyperbolic orbit. So let's see what we've got. One last time, the big takeaways here. We have the Kepler law orbital equation. It is the polar form of conic sections, characterized by kind of 2 properties. P sets the overall size of the orbit. It's the semi-latus rectum, but it's made out of things like the total angular momentum of the system and some constants. Eccentricity sets the shape of the orbit. It's a dimensionless number between 0 and infinity, but basically based on how it relates to the number 1 will determine the shape. And we can see that it can be calculated directly, again, from the constants of interest here. So I think that's a pretty good summary of where things come from the Binet equation, all the way up to our final orbital calculation for the Kepler inverse square law of gravity. And in future videos, we'll look at a few other instances of this. We'll use it, we'll answer some more general questions, or maybe actually more specific questions about particular behaviors, and really see the utility of thinking about these Kepler orbits. QED.